In this video, I'm going through the Extension 1 2023 HSC exam question 14, so the last question. Question A, the first part of that question. Interesting one about inverse functions. Interesting because we're trying to find, in the end, a value for g-2, so the derivative of an inverse function, without actually having the inverse function. So quite a cool little question. The first one's worth 1 mark and the second one's worth 2. So the first one's obviously a clue saying explain why that particular function here, fx, is an inverse function. So we'll go into that one first. So here's the actual original function. It's actually pretty easy question. It's an example of how you can get a mark pretty easily in the last question. So here's y equals 2x, here's y equals log x. So if you're adding them together, like this is increasing and this is increasing, so clearly you could just explain that they're both increasing, meaning that this one, when you add them together, will also be increasing all the time, or also known as a one-to-one function, could also be decreasing. So that's probably the go-to for me. I always like to graph things if it explains it nicely. The other one, to show that it's, so we're talking about it always going this way, always increasing, whether it's going concave up, concave down, no one really cares, as long as it keeps going up. So the other way, and probably the most algebraically easy way to do it, is to differentiate this thing, because it's pretty easy to differentiate that. And then you get 2, and then 1 over x, and they're both always going to be positive. So the whole thing's going to be positive. So if the derivative is positive, it means it's always increasing. So it definitely has an inverse. The inverse of this will definitely be a function, I should say. Okay, in the second part, I actually asked, and you do use that first part, by the way, the derivative bit. You're trying to find the derivative of that inverse function for a particular value of x. So and that's kind of key, what this is. But I give you a pretty big clue here by considering the value of f1 or otherwise, which means pretty well always do it the way they suggest. So subbing in, it's really easy to get 1 mark here. So in fact, 2 marks in question 14 would have been easy, but just subbing in 1 into fx and see what you get. So let's do that first. So I actually did that down here. So you're subbing in 1, f1, which just means all you're doing is subbing it in for x, and you actually get a value of 2, because you get 2x plus log 1. So you get 2. So that's important. So that means, this is what this is used a little bit later, for fx, for the original function, when x equals 1, obviously, y equals 2. And that means that for the inverse, of course, you swap them around. When x equals 2, y will equal 1. So you're swapping around the values. That's key a little bit later. Okay, so let's get into the question. That's the hint. That's just doing exactly what they asked you to do. So here's the question. We're given the original function. We're calling that function, or we're calling the inverse of that function gx. So we can work with just gx. So that means, and there's a couple of ways you could do this, but this is a nice way to do it. It means that gx, which is the inverse, and fx are inverses of each other. In other words, they undo each other. So it means that, because you want to be able to differentiate something, you want to differentiate gx. So what is gx? So gx means if you substitute in fx into where x is, you will get x. They undo each other. And that's kind of key. Like this step here is not trivial. This is a very nice step because it gives you something to differentiate, because we want to get g-2 right down here. So you want to be able to differentiate gx, which is gfx. Now, how do you differentiate gfx? Well, it's the composite rule. It's the fat finger rule. I call it fat finger rule. Function of a function rule. Chain rule. Lots of names for the same thing. You differentiate the outside, so you get g-fx, and you also times by the derivative of the inside. And equals, and you differentiate the other side, differentiate x, you get 1. So that means we have an expression for g-fx, which is 1 over f-x. So now we want g-2. So we want that to be 2. In other words, fx is 2. So let's go back to what we had a minute ago. For fx, when x equals 1, y equals 2. So this is y equals 2. So that this is saying that x equals 1. We know x equals 1. So g-2 actually equals, putting in here, it equals putting in x equals 1. So I put in a 1 there. And it's not quite finished, really close, because you've got to say, what is f-1? Well, do we know f-x? Yeah, because we did it in the first part. The derivative of 2x plus log x is 2 plus 1 over x. And then you sub in 1 because you want an f-1. So you get 2 plus 1, so you get 3. So it's actually 1 over 3. Nice, simple little question that on the surface is really hard looking.